All right, can everyone hear me? Okay, so my clicker is not working, so I'll stay close to my laptop. All right, so hi everyone, my name is Jackie. So I just graduated from MIT and I'll be joining NY Eastern after this program. So let me first talk a bit about algorithmic fairness. So I'm sure everyone in this room is aware that kind of data-driven algorithms can have a huge impact on society. And so I think of the broad question of algorithmic fairness as when algorithms exhibit some sort of undesirable disparity that in turn has some impact on society. And there's many ways in which undesirable disparities can arise and many types of disparities. But I'm going to be focusing on one common one that happens in the machine learning setting which is that the common source of disparity is the fact that data sets that algorithms are trained on are often kind of non-representative of the population that we're interested in. So to give you a concrete example, precision oncology is the study of kind of personalizing cancer treatments. And there's some concern that the emergence of precision oncology might actually deepen inequalities in the healthcare system. And the reason for this is, or one of the reasons for this is that kind of genomic sequencing efforts overwhelmingly represent people of European descent. Right? So essentially what this is saying is that there was some sort of bias in the data generating process. And so an algorithm trained on such data might not perform well for like all subpopulations. And so if you look at the typical approach of the algorithmic fairness literature, the typical approach is to modify the algorithm so that its output is more fair for some definition of fairness. But if you look at the problem of, if the source of the problem came from the data, then modifying the algorithm is not really going at the root cause of the problem. And so one obvious approach to tackle this problem is to simply collect more data, right? Or collect more representative data. And of course, this is not an easy thing to do, but I claim that sort of one natural way to collect more data is to simply continue collecting data after we've deployed the algorithm and sort of try to continuously update our algorithm. And in the machine learning space, essentially this idea of continuing to collect data and updating our algorithm is essentially the idea of using online learning, right? So in online learning, the algorithm can try to quote unquote, like obtain better data in order to improve the policy in the future. And by obtaining better data, we essentially mean kind of like trying all different actions so that we have enough data and better estimates of all possibilities that for our learning task at hand. So essentially what I'm saying is that simply using online learning is a reasonable solution for some algorithmic fairness problems. And sort of this is a theoretically grounded claim because there are many sort of exploration-based algorithms that are known to theoretically converge to the optimal policy in many settings. So here I just mean that if a policy has sublinear regret, eventually the policy is always going to pick the best action. And this is what I call the optimal policy. But to get to this upside, the downside is that exploration is actually costly in the short term. And this is the essence of the exploration-exploitation trade-off that I'm sure many of you have heard about. And so basically, since exploration is associated with a cost, so who incurs this cost? Well, it depends on the setting, but like, for example, in the medical setting, it'll be the patients because let's say you have a new drug and you want to learn whether this new drug will be effective for this population, then you essentially need to try the drug on some patients. And if the drug wasn't very good, then these patients kind of suffered this cost of exploration. So essentially, what I'm saying is that I think about online learning essentially as a kind of like a cost allocation problem, right? So exploration is something that's necessary, it's associated with the cost, and some people have to incur this cost. And different bandit algorithms or different online learning policies might allocate this cost to different populations. So in our work with my advisor, Baek, what we do is we study how to allocate this cost of exploration in a quote unquote fair manner. So I'm going to kind of briefly describe the main results of this work. So the first result is that we show that canonical algorithms like UCB are unfair. And to explain what I mean by this, let me give you let me walk through a very simple concrete example. So here in this example, we have the canonical multi-arm bandit problem, like the K-arm bandit problem with 3 arms, but I'm adding the notion of groups. And here, the notion of groups, there's groups A and B. At each time step, one of the 2 groups arrive. And this bipartite graph specifies which arms a particular group has access to. So if group A arrives, the central decision maker has to assign them, has to take one of the actions that are available for this group. So this is a very simple example with just 3 arms and 2 groups. And in this example, only arm 2 is a shared arm between the 2 groups. And so if we want to learn about arm 2, we can either get group A to pull it, or we can get group B to pull it, and so on. But if we assume, let's assume that the rewards satisfy this relationship. So arm 2 is actually the worst arm, followed by arm 1, followed by arm 3. In this case, you see that there's actually an asymmetry in how much regret is incurred when both of these groups pull arm 2, right? Because essentially the other option for group A is worse than the other option for group B. And so if, as a central decision maker, I only cared about minimizing total regret, I actually want group A to pull arm 2, because we get the same amount of information regardless of which group pulls this arm. And so we show that any algorithm that tries to minimize total regret, like UCB, in this example, all of the regret is going to be incurred by group A, and essentially 0 regret or constant regret is going to be incurred by group B. And this is, in some sense, kind of the worst possible outcome in how this cost of exploration is allocated between these 2 groups. Like all of the cost is incurred by group A, 0 cost is incurred by group B when you use UCB, right? Or basically any algorithm that tries to minimize total regret will essentially try to identify the subpopulation who are the cheapest to explore with. So how we address this problem is that we formalize a notion of fairness via a Nash bargaining framework. And so I won't go into the details of this, but basically the main idea is that we define a utility. We have to define utilities for each group to use this framework. And how we define it is that we define it as the decrease in regret compared to if the group had to explore on their own. So in the previous example, group B, if group A didn't exist, like group B would incur some amount of regret because it still wants to learn about arm 2, so it has to pull it. So we kind of normalize using this idea of when each group has to explore on their own, how much group they would incur. And we define utility as like how much your regret decreased compared to this benchmark. So I won't go into the details, but essentially we show that an algorithm exists that kind of satisfies this definition of fairness. And then we show that the price of fairness is small. So basically satisfying this notion of fairness, it's not going to minimize total regret, but it will only increase total regret by a small amount. Okay, so this is like a very short summary of this paper, but I'm happy to talk about this more often. So now I just want to talk about some future direction. So the high level idea of this work is that we are essentially thinking about exploration as an allocation problem and sort of thinking about how to allocate this cost to different groups. And so let me talk about some interesting questions, some questions that I think are interesting. So the first direction, which is like kind of a practical high level question, is essentially the question of when should exploration actually be used. And I'm interested in this question because I think exploration is something that's not that prevalent in practice, like whether that be algorithmic systems or non-algorithmic systems. So for example, take the hiring setting. Like if you're hiring someone, like usually you're not going to hire someone just for the sake of learning about this person, even though that they're probably not going to be that good, right? But it is the case that so I think like greedy algorithms are very prevalent in practice. And fortunately, it is the case that greedy does work well under certain regimes. So it was shown both theoretically and practically that greedy works reasonably well. But outside of these regimes, it could be that greedy can lead to systems being stuck at some local optimal, right? So there's this nice paper by Danielle Lee and others that study the hiring setting, and they actually show empirically that if you incorporate exploration, you can actually improve both the quality and the diversity of new hires compared to using a greedy algorithm, which essentially shows that in hiring, actually, like this kind of phenomena is going to be prevalent. So along these lines, I think a couple of questions that could be interesting are sort of one, kind of understanding more granularly in what ways does kind of greedy fail. So is it the case that certain subpopulations will always be worse off if you use greedy and while other populations are better? Or is it the case that kind of everyone is worse off and so on and so forth, kind of really understanding what greedy does in these settings? Another question is sort of one, the argument against exploration is that it's associated with a short-term cost. Okay, so then maybe can we quantify this short-term cost of using exploration compared to just using a greedy algorithm? So like, how long do we have to wait to reap the benefits of exploration? And then lastly, another direction that I'm interested in is also kind of understanding when sort of multiple agents or multiple platforms kind of face a similar bandit problem. So for example, if the platforms are collaborative, this is the idea of sort of meta learning, and then we can get like, better learning because we have like multiple data sources. On the other hand, if the platforms are kind of strategic about like what bandit algorithm they use, then sort of what happens then? And there's also been some recent work where like users can also be strategic in choosing platforms, and then you can form some kind of equilibria. But essentially in all these questions I'm interested in, is learning going to be efficient? And also how is the cost of exploration kind of divided amongst these different agents? And that's it. Thank you so much.
Thanks for the great talk. Questions?
Yes, thank you. Wonderful talk. I have a question. Right? You mentioned one way is to get new data. Another way, which I would like you to comment on how that would compare, is to reweight your data. So I'm just thinking that, well, I used to work at Microsoft. We had Xbox data, and we tried to use it to predict sort of elections. And we realized there are all these young males on Xbox and very few old female women, but to predict elections, we needed the old female women. But it turns out there were still thousands of old female women on Xbox. And by reweighting the population to recreate sort of, so you didn't even need to collect new data. So in this database, if I had 10% of a certain population which is not of European origin, but if I would in all my algorithms just put a weight on my data and sort of make sure that I weigh enough the data of the underrepresented group, that could sort of mitigate some of the issues, because now you would learn how to treat cancer for people who have a darker skin or a different skin color or things like that.
Yeah.
So can you comment on how that, because that might be much easier than creating sort of finding 5 million people of African origin in your database for DNA?
Yeah, good question. Yeah, so I think reweighting data is essentially a method of improving current predictions with the current data set. So I kind of think of reweighting data as just finding a better machine learning algorithm, whereas maybe the current machine learning algorithm, we just try to minimize like mean squared error over the whole population. And maybe if you reweight data, you're kind of saying like, oh, we also care about predictions, like doing well on predictions, like in each subgroup. But I feel like ultimately what we want is like best predictions for everyone. And I think like reweighting data can only get you so far, right? So like when you reweight data, there's like a trade-off of like, oh, like, this in certain subgroups you might do better, but in certain subgroups you might have to do worse. And I think, so I think of this as like, okay, you're actually trying to improve the machine learning algorithm to get better predictions, but ultimately you do need more data if like the ultimate goal is like you want kind of best predictions for everyone. Yeah.
Okay, thank you. Yeah. Maybe one more question.
Great work, very interesting. I think the idea of specifying utilities for different groups is brilliant. I'm just curious about, do you already know the labels of the groups for people? And what happens if you don't actually know which group people belong to, if there are latent group labels?
Yeah. So in this work, and I would say like most of the prevalent work in the algorithmic fairness, like we assume that groups are given, and in this work we do assume that the group identities are known. So I think, and I think this is reasonable in that like a lot of the work on algorithmic fairness, like the problem really is boils down to like certain subgroups that were kind of historically disadvantaged. So there is kind of a natural notion of groups, but I think understanding. But I think like like the problem of algorithmic fairness where you don't know groups, kind of along the lines of like multi-calibration, which is what we talked about in the boot camp, is interesting, but it's like, yeah, well, we don't have this assumption, but I think this is an interesting direction to kind of understand what happens when you don't know the group labels. Yeah.
Thanks.
Thanks. Let's take further questions offline. And the final talk of the session will be given by Kang-Ning Wang on approximately efficient bilateral trade.